present the work that I performed jointly with my co-authors Claudio Fontana and Alessandro Nuato last year in Padova, which deals with a sophisticated class, a fascinating class, class of stochastic processes, which we name CBI-time-changed Lévy processes, and we henceforth we're going to use the acronym CBITCL processes. So then just to give you
peut-être il faut viser le clé USB.
Thanks. And just to give you a few definitions, not a lot, but just to give some context, maybe for the non-experts in the audience. For example, just we consider quality space. All of you know what a quality space is. Just if you have any questions, just you can ask me. Okay. Very simple. And actually, this class of stochastic processes has a very main building block, which is a Lévy process. But a Lévy process, actually, there is a very definition. I'm not going to use the very definition. Actually, I would like to give you some intuition about the trajectories that a Lévy process exhibit over time, which is actually one of its main characterizations that are used by the experts in the field. For example, consider time. This is notation to denote a stochastic process. A stochastic process is just a fancy word. It's just a fancy word for a random function, which means that at each time t, the function evaluated in t is a random variable. This is just pure, plain and simple, as you saw the notion of random variable, I'm sure, before during your graduate studies. And actually, the stochastic process L, which is CAD-lag. CAD-lag, it means that it can have jumps at times over time. Then we say that L is Lévy process if it can be represented as follows. Maybe did you see? Yeah. And you have three different parts which are independent in the sense of classical independence between random variables. You have the drift, which is the deterministic part, plus the Brownian motion. You all know what Brownian motion is, right? Which is the first source of randomness in the trajectories of the process, plus the let's say the jump part, which gonna generate the jumps of the process, which are gonna be random, and which is one of the reasons why it is a CAD-lag process. Actually, we have depending on its parameters, we have different possibilities to represent the jump part. But in this case, for the construction of our main building block of this class of processes, which is going to be the continuous state branching process with immigration, CBI process, we're going to consider two different types of Lévy processes, an increasing one and a finite first moment Lévy process. in the case of a finite first moment one, the jump prop takes the following form, which is this way. This guy, it represents the jumps of the process, but actually it has to be compensated for technical reasons. So I'm not going to enter the details at this point. This is for this is called the Poisson random measure, which counts the jumps over time of the process, and it has its intensity. It depends in this case of the Lévy measure pi, just the compensated. You can see here the jump intensity of the process is totally characterized by this measure pi, and this Lévy measure satisfies the first moment, the finiteness of its first moment, which means in this case, in this setting, we're going to consider only Lévy processes which generate non-negative jumps, which means that it can jump only upward. For example, you have this. Just an example, okay? It has its condition. You see? Okay. And another configuration is the increasing Lévy process. In this case, we have to remove the Brownian part, although because the Brownian part fluctuates very strongly, and it's going to break the increasing property. In this case, the Lévy process, the following form. There, to integrate over x. And in this case, increasing Lévy process, the parameter b here is non-negative, and its jumps are of finite variation. Here, it's characterizing Lévy measure mu has to satisfy the following condition, finiteness condition. This way. Then, actually, when you have a Lévy process, you can also characterize it by means of its characteristic function. And this is just, can I write it there? Do you see? It's Lévy, we call it the Lévy exponent, and actually it has a very general form, but in all specific cases, this guy here, in the case of the spectrally positive Lévy process with finite first moment, it has a very specific form. is denoted by phi. Phi of P. Then you can recover the drift parameter and also the coefficient of the bounding part, and this is the phi here, and which is just defined. Actually, it can be extended to a maximal domain, but in this case, it's defined over the negative real line this way. And for the I just take some time on the definitions because it is very important to understand the sequel. And for the increasing Lévy process, its Lévy exponent psi this time has the following form. Then on these ingredients, we can define a further sophisticated process, which is going to be built upon our Lévy processes, or two Lévy processes, and is going to be totally characterized by these two functions, which are themselves characterized by these parameters. Then we have to, you just have to choose the B, sigma, pi, the Lévy measure pi, which I will call the first mode fineness condition. And in this case, the immigration part, you have the drift, also the Lévy measure mu that you can choose also while paying attention to its condition. Then on these ingredients, we define what we call continuous state branching process with immigration, whose characteristics are the immigration mechanism, this function, and the branching mechanism, this function. And it is defined, actually we have several different characterizations, but the very definition of the latter is the following. It is defined by its Laplace transform here as a exponentially affine function with respect to its initial value. For example, you take at time t, you consider the Laplace transform of the process, and it is given by an exponentially affine function with respect to its initial value here. And the coefficients of this function are given directly by the characteristics of the process, namely psi, this function, and pi. And actually, they depend on another object, which is the function v, which is given by the Newton solution to this ordinary differential equation, depending on the branching mechanism here. Well, in this case, it is totally nonlinear, but in very specific cases, we can have maybe a semi-closed form for V, or maybe use some numerical scheme to determine to determine the function V. Just a brief history of this class of processes. It was first introduced in 1971 by Kazu and Watanabe, initially as the result of a limit of a strong limit theorem regarding a class of discrete processes called the Galton-Watson branching processes with immigration. And then in 2001, Filipowicz was the first to apply CPI processes to finance, but in a very specific context, in particular, the interest rate modeling. He characterized affine term structure models. I'm not going to enter details. And in particular, he extended the well-known CIR model for the short rate by including particular jumps and by observing that the CIR process is just refers to the continuous part, to the continuous version of a CBI process. But the CBI process can be far more general, insofar that it can generate jumps, only upward jumps, but of very different structural properties. For example, depending on these functions, I emphasize phi and psi. Then later, in 2003, Jufrey and his co-authors introduced the class of more general affine processes, and CBI process revealed to be a fundamental subclass. In 2006, actually, this paper is going to be key for the construction of our novel stochastic class of stochastic processes. Personally, derived a characterization depending of a stochastic integral representation of a CBI process. If you recall the representation of a Lévy process with respect to a Brownian part and a germ part, actually it's very similar to that to these representations, but you can but actually they are more sophisticated as the jump intensity can depend on the state of the process itself, which is a peculiar characteristic of CBI processes. And then in 2013, which is actually our first motivation for the introduction of the class of processes I'm going to present today, Caballero and co-authors extended the Lamperti transform, which was initially defined for continuous state branching process without immigration, which means this part is equals 0, and they extended this Lamperti transform to CBI processes. Actually, it means that if you consider the CBI process defined as before, which is Skylab, non-negative, and which then generates only non-negative jumps, namely upward jumps, then it can be represented as the solution of a stochastic time-changed equation in the following way. Then you have a CBI process, and you have two independent Lévy processes. Then your CBI process can be represented by this stochastic time-change equation. Can you see? You tell me if you have any question. This Lévy process represents the immigration of the CBI process, which is the increasing Lévy process, characterized by this function. And this Lévy process refers to the spectrally positive Lévy process with finite first moment, which is characterized by the branching mechanism here. And you can notice the presence of the integral of the CBI process here, which is well defined because I recall the CBI process remains non-negative over time almost surely. And actually, Caballero and co-authors showed that there exists a unique, strong solution to this equation, which is a CBI process. And when you have a CBI process, conversely, you can extend the probability space such that there exists two independent Lévy processes having these characteristics such that your CBI process in this extended probability space is given by this. Okay. Sorry.
Clarifying question. What is meant by strong solution to this time change process? Is it like any L1 and L2 or?
Actually, L1 and L2, actually they have to be independent, and actually they have to satisfy very specific conditions. Like I said before, they have to have these characteristics. They have to be independent. This one has to be increasing. This one has to be spectrally positive. When I say strong solution, it means that when you lie in a given probability space, having its own filtration, then there exists a unique strong solution X, which is measurable with respect to the filtration generated by these two Lévy processes. Actually, strong in the sense that the two Lévy processes are given initially. Okay. I just spent time on this because this is the very motivation for the class of CBI-TCL processes. And if you have some intuition from this, you can understand in a better way how the CBI-TCL processes are constructed at the very beginning. Then from 2017 onward, CBI processes have experienced a renewed interest in financial modeling, in particular by observing the presence of jump clusters in different sets of time series in finance. For example, regarding the short rate, or maybe the price of electricity over time. And Zhao and her co-authors published some papers on this, where they applied CBI process to model the short rate, motivated by the fact that they are observed jump clusters, and the CBI process can generate jump clusters. And also they applied it also to energy modeling and to the modeling of volatility. And more recently, I and my co-authors, we applied CBI process to model the hierarchy of multiplicative spreads on the interest rate market, and also to model the different exchange rates on the market. In particular, when constructed a financial model for the exchange market, you have to be careful because several probability changes are required, and you have to derive probability changes that preserve the structure of the process. And because of the properties of CBI processes, we can derive a Gaussian type result, which gives a very tractable probability change, which we have applied with success to the FX modeling. Just to give you two simple examples of CBI processes. If you recall the representation of Lévy processes, in this case, for the CBI process, we have the state dependency compared to the Lévy process. For example, for the continuous CBI process, which refers to the CIR process, you have this part here, and the time is represented by the time interval of the process, which means that the fluctuation of one in motion are controlled by the evolution of the process itself. And the second one is a bit more sophisticated in the sense that we have, in addition, a jump plot here. In particular, these are just examples, specifications of this case. For example, for the first one, the Lévy process one is just the drift, beta t, and the spectrally positive Lévy process is just the drift b plus the volume part, to which we have applied the time interval of the process. And for the second example, the Lévy process 1 remains unchanged, but the Lévy process 2, which represents the spectrally positive jumps, we have the jump part in addition. Actually, this is if you recall, this is the jump part which is represented by a Poisson measure, and actually this part up to modulo some space extensions is just equivalent to this guy. You have a Lévy process, compensated spectrally positive alpha stable. Alpha stable, it means that we have chosen a very specific form for the Lévy measure pi, to which we have applied the time interval of the process itself, which is just this guy. Okay. You have the form here for the Lévy measure. In this case, this characterizes the fact that it is an alpha stable CBI process. Just to give you a sample path, you can observe the non-negative jumps, namely upward jumps, for example, here, and here. And also you can also observe the self-exciting property of CBI process, which means that in the sense that the jump intensity of the process is proportional to the process itself, if the process itself experiences an upward jump, its value is going to increase, and then the jump intensity, as it is proportional to the process itself, is going to increase as well. And then if you have a bigger jump intensity, the likelihood of your subsequent jumps is going to be higher, and then you can observe this here. You have jump clusters. Now the core of the work that I'm presenting is the construction of this class of processes, which we call CBI-time-changed Lévy processes. Now that you have discovered these ingredients, this definition is going to be more intuitive for you. The CBI-time-changed Lévy process is just a two-dimensional stochastic process, x, z, CAD-lag, where the first coordinate x is a CBI process and the second coordinate z is a time-changed Lévy process. Here, you just have define it as follows. And why actually this is just the time interval of the CBI process. Just to be more specific about a time change is just a proxy for time. To find a proxy for time by means of a stochastic process, your stochastic process has to be increasing because time is increasing, and also non-negative. And then in this setting, we propose an increasing process, an increasing process that mimics the evolution of time over time. And this is just the time interval of the CBI process, which I recall we made non-negative over time almost surely. Also pay attention to this. This Lévy process is different from these Lévy processes which characterize the CBI process. this Lévy process is an additional Lévy process of characterized by a new Lévy measure gamma here, on which we do not impose any conditions. And in this case, we have simplified the setting because we have chosen the Lévy process L independent of X, which means independent of these Lévy processes. But actually, we can have dependence between both by constructing the CBI-TCL process in the following way. We just have, for example, to consider a two-dimensional Lévy process. Characterized by a Lévy measure applied to a two-dimensional set, which means that these coordinates are not independent. They can generate jumps simultaneously, and actually we can directly build upon the Lemperti transform of the CBI process. For example, we suppose that we are on a probability space on which there exist three Lévy processes, an increasing one and a two-dimensional one, independent. Then we construct our CBI process as the strong solution of this stochastic time-change equation, and we construct our CBI-time-changed Lévy process by referring to this two-dimensional process where the first coordinate is the freshly constructed CBI process, and the second coordinate is the time changed of this Lévy process by the time interval of the CBI process. This is the framework that we have developed in our paper. But just to make things easier, we can suppose that they are dependent in the context of this talk.
Just one question.
Yes?
Why would you need that? So you have a CBI-time-changed Lévy process, but why would you need an additional Lévy process time change like the L2 in the Résumé class?
Just actually, the motivation comes from finance. Imagine that you have a financial model to represent the price of a stock. Then your stock, most of the time, your stock remains positive, and we represent it by the exponential of a process which represents the log price. And the log price, it can be negative, right? It can have negative jumps. It can have as many negative jumps as positive jumps. And in this case, it's motivated by this. Actually, this guy, the CBI process, which remains positive and generates only upward jumps, represents, for example, for a stock, it represents the proxy of volatility, for example. And Z, it represents the log price of the stock.
The price of volatility can also jump down. I mean, it's not very likely.
Yes, actually, yes, but it remains positive, right?
Yeah, sure.
Yes. Actually, it depends how you model volatility, because in this case, it's if you define if you consider a financial model for volatility, the CBI process here is thought of as activity rate, you know, and then for see actually it doesn't represent the volatility directly by itself, but the activity rate of volatility. Yes. Then, for example, when you have an upward jump, it represents periods when you have more fluctuations, for example, and then it decreases, you know, by the compensation. It should be thought of as this way. Actually, it is just one motivation among others. This class of processes can be applied to many other things. For example, I don't know, the evolution of a particle, for example.
So you agree that CBI-time-changed Lévy process, then it's a three-factor model? given by 3 Lévy processes can fully be characterized by 3 Lévy processes.
When you consider the very definition, yes. But actually, yes, but the CBI process actually it depends. When you consider the CBI process here, actually, when you see it, when you see that the very definition is a three-factor model exactly, because you have this when you consider the vector of Lévy processes, you have 3 factors. You have the first one, increasing the Lévy process, and you have this guy. But these 2 Lévy processes are not independent; they are dependent because they depend on a 2-dimensional Lévy measure. Okay. But at the very beginning, it is built on a 3-factor process. Yes. In particular, on motivation, like just said, it comes from financial applications. But like I said, it can be applied to many other contexts. In particular, it builds upon the following contribution. This is right. This is the works that motivated at the very beginning the introduction of this class of processes. Then, just to give you the outline of this talk, the things that I would like to talk about. Actually, the first part is the most important part to me because it contains the foundational results for CBI-TCL processes. In particular, we have the characterization by means of its dynamics, which extends the Dawson-Lee representation of a single CBI process that I talked about in the beginning of the presentation. And also, actually, we relate it to the class of affine stochastic volatility model, which is a more general class of stochastic processes. Actually, we can easily prove that our CBI-TCL process is an affine process, and then by means of its structural properties, it directly enters the class of affine stochastic volatility models. But the other way around, considering an affine stochastic volatility model, we under very specific conditions, we can show that we can recover a CBI-TCL process by going from a more general process at the beginning. Then we have derived further results for CBI-TCL processes, specifically motivated by mathematical finance. In particular, with a view to model a stock on the market by means of a CBI-TCL process, and to do some pricing on it, we need to characterize its exponential moments by means, because pricing can be done by representing the price of a product on the market with respect to a Fourier representation. And then we have derived conditions, and under further but very mild assumptions, we have characterized the exponential moments of a CBI-TCL process along with their explosion time. And we have also determined the asymptotic behavior, in particular concerning a single CBI process. Its asymptotic behavior is very well known in the field. But regarding this part, the time change part, it's more complicated to derive results. But actually, under very specific assumptions, not that strong, which actually follow the specifications used to derive the results on their exponential moments. We have derived the asymptotic behavior of this time change part. Then if time permits, I'm going to spend some time on them and maybe just to present them briefly. And for the third part, I don't think that time is going to permit it, but actually, like I said before, we have applied our class of CBITCL processes to the modeling of an exchange market where probability changes are most of the time required. Actually, we have derived under very mild assumptions the probability change that preserve the structure of CBITCL processes, which means that when you perform your probability change and you consider the CBITCL process, which your two-dimensional stochastic process, which was the CBITCL process under the first probability, then we can show that it remains a CBITCL process under the new probability. And this is crucial when constructing and playing around with the model for exchange rates. Then in these slides, I have a simple example of CBITCL based financial model. I don't think I will have time to enter details regarding that one, but I'm just gonna maybe show you it briefly because it just corresponds to the simple examples of CBI process that I have presented in the introduction. Then, regarding our first foundational result for CBITCL processes, actually it extends the Dawson-Lee stochastic representation of a CBI process. Just actually, the characterization consists in expressing a CBITCL process as the solution to a two-dimensional system of stochastic differential equations. Just we consider some ingredients which are very similar to the ones that I have used to represent all Lévy processes, if you recall. Maybe I can give some. First, we have to consider two Brownian motions and two Poisson measures, but this time, unlike Lévy processes, these Poisson measures have to be defined on a three-dimensional set. For the first one, we have the positive real line, power 3. And the second one, you add the positive real line times r, the whole real line, times the positive real line. Actually, this r, it corresponds to the fact that for the time change part of the CBITCL process, if you remember the Lévy process, its Lévy measure has no imposed conditions on itself. Actually, your Lévy process can jump either upward or downward. Actually, the presence of this R is the consequence of this. You can be convinced by here. We cover the Lévy measure of the Lévy process of the time change part. Well, actually, this is quite technical at first sight, but it's just a more sophisticated version of the of the representation of a Lévy process. But in this case, for the CBI process, this representation is very famous. It's called it is due to Dawson Lee, the paper, the 2006 papers that I talked about in the introduction. And you have your jump part here, and you can observe the presence of this integral, which represents the fact that your jump intensity depends on the process itself. And this guy Z, which represents, if you recall, the time change part, the Lévy process time change by the time integral of the CBI process. In this case, you have two separate parts for the jump part, which is due to the fact that we have no impulse conditions of the Lévy measure here. But on the Lévy measure part, we have a finite first moment condition, which means that we have just one element for the jump part. In this case, you can see that the jumps of the second coordinate of the CBITCL process Z, their intensity directly depends, similarly to the jump intensity of X. They depend on X as well, which means that the jump intensity of Z is totally dependent, totally proportional to the process X itself. Then our first foundational result is the following. If you consider CBITCL process XZ as defined before, the very definition, actually we can show that it is a weak solution to the previous system of stochastic integral equations. Weak in the sense that you have to extend the space probability on which there exist the ingredients showed before, and your CBITCL process on this extended probability space is a solution to the previous system. And conversely, if you consider directly a probability space on which you have directly this system of stochastic differential equations, we can show that there exists a unique strong solution, XZ, which is itself a CBITCL process. Then I'm not going to enter the details of the proof. Actually, it just consists in playing with the space extensions, Lévy Ito decomposition of a Lévy process, and also playing with the time changes. And it can get quite technical at some point. Then, as a first result to our second foundational result for CBITCL processes, we can easily show that the CBITCL process XZ, the two-dimensional one, is itself an affine process, as in particular similarly to the CBI process itself, which then in this case has a state space of this form, the positive real line representing the CBI process, and the whole real line representing the second coordinate Z, which can live in the whole real line differently from the CBI process. And the Fourier Laplace transform of this process, which is the characterization of an affine process, its coefficients directly depend on the characteristics of the CBITCL process. In particular, we cover the integration mechanism here, side, the branching mechanism, and this guy is just the Lévy exponent of the third Lévy process. If you recall. It's just the Lévy exponent of this guy, okay? And actually, when we consider a more general affine process, which is called in the literature affine stochastic volatility model, actually this is just an affine process characterized by a Laplace Fourier transform of this form, but the function u and v the function u and v are not directly given by this system, actually, because we don't know if it's a CBITCL process. Actually, we can show that this more general two-dimensional process can be a CBITCL process under some very conditions. If you know a bit about stochastic calculus, for this process to be a CBITCL process, we have to show that its covariation is equals 0. We have to show that this Lévy integral is finite, where this measure M1 appears in the compensator of the jump measure of the more general process, which is, because it is affine, it is also a semi-martingale, and there is a strong theory well defined on these types of processes. And we have also to check that Z is almost surely constant on every time integral, such that the time integral of the first coordinate equals 0 almost surely. But I'm not going to enter the details of the proof, but actually the key step to prove this result is just to say that an affine process is a semi-martingale, and then by means of the semi-martingale theory, you can express the correlation between the two coordinates by this form, and you just inject step by step the conditions to derive a certain form for the characteristics of the semi-martingale, which gives you the CBITCL property. Then just to give you more specific results, actually, because they are directly motivated by financial applications, for example, the characterization of exponential moments and the asymptotic behavior of the CBITCL process, but actually they can be applied to a more general context. We have to define some preliminary notation. If you recall the form of the functions psi and phi, actually they are defined on the negative real line, but as convex functions that can be extended to a common effective domain, which is going to be of this form. And we can proceed similarly for the Lévy exponent of this Lévy process. And actually, under a finiteness assumption of the function phi at the boundary of dx, particular evaluated in this guide, we can extend the affine representation of the CBITCL processes in this way. For U1 and U2 extended going beyond the negative real line. Because if you remember, in this setting, well, in this context, it is defined with complex numbers, but when restricted to the reals, for U1 it has to be negative, and U2 actually it can just be 0. Then, by means of quite technical results by Keller-Russell and Meyerhofer, we can extend this affine representation to the effective domains that I mentioned before. But actually, they depend they depend on potential explosion, which is characterized by this maximal lifetime, which represents the maximal lifetime of the functions u and v. And actually, the characterization of exponential moments of the CBITCL process just reduces to the characterization of this time of explosion for exponential moments. Then we can characterize it under without any further assumptions, just the mild assumption on the finiteness of phi, the branching mechanism on the boundary of dx, and we depending on the locations of u1 and u2, and also of this guy, which represents the supremum of this set, which can be actually, it can be depending on the context, and can be we can derive it quite easily. Then we can say whether it is infinite. Actually, what we would like to have is an infinite time of explosion, and in which cases we have a finite time of explosion. This is the case that we would like to avoid. Well, actually, the natural question that that rises up at this time, well, it's quite technical to verify these conditions in practice. For example, when you have a financial model and you want to verify if your exponential moment for pricing may explode at some point. And actually, we can, under a very mild additional assumption, we can derive we can have the time of explosion which is infinite for all u1 in dx, if and only if we just have we have this condition on the branching mechanism at the boundary of dx plus the Lévy exponent of this Lévy process at u2, which is negative. Actually, this condition, in particular, in the paper that we have written conjointly with my co-authors for the modeling of multiple yield curves, this condition can be quite easily satisfied because actually we can have all of our times of explosion infinite under this very mild additional assumption, the finiteness of the immigration mechanism at the boundary. If and only if we just have to satisfy, for example, under some specification of the CBI process and the Lévy process. In this case, we know the closed form of the branching mechanism and of the Lévy exponent. Then we just have to check, or maybe to impose on some parameter this condition, and we're going to have all the times of explosion and infinite for all u1 in dx. Then just to give you, still have time, or Shiva? Okay. Just to give you the asymptotic result for CBITCL processes. Actually, we do not need any additional strong assumptions. We just need the mild assumption that we had to impose on phi for the characterization of exponential moments. And then, but actually, well, I forgot about that one. We need that our phi, the branching mechanism, is strictly subcritical. If you remember its form, actually, it has a drift part, and actually we need to impose a positivity condition of on its drift part. Then under these conditions, we can show that the functions v and u have this behavior in the long run. which in particular characterizes the behavior of the time change part, which is the part that poses problems when dealing with the asymptotic behavior, because the asymptotic behavior of the CBI process is well known. Then, under these conditions, we have this asymptotic behavior for the time change part, which in particular can be totally derived in a very simple specifications, because it just depends on the integration mechanism and on this guy, which is the limit of the function v. And actually, we can show in particular that this guy represents the exponent of a Lévy process. Just to give you quickly the form of our CBI-TCL preserving probability change. Well, as before, we have to introduce some notation. I'm not going to spend time on this.
You can just kind of give the result there.
Yeah, okay. Actually, this is just almost the same assumptions as before. We always need this mild assumption on phi, which is the finiteness of its derivative function at the boundary of dx. Then actually we can show that we can derive an equivalent probability measure whose density has the following form, and under which our CBI-TCL process up to some time horizon that we have introduced beforehand remains in the same class but with modified parameters. But actually these modified parameters can be easily derived by means of on the characteristics of our CBI-TCL process at the very beginning. By this I mean it's the Lévy measure pi of x, the gamma Lévy measure, the Lévy measure gamma of this Lévy process, for example. Actually, as a direct consequence of this result, we have a necessary insufficient condition for the martingalité of the exponential of the time change part, which is most of the time an indispensable requirement if you want to build upon our CBI-TCL processes a financial model. Yes, then I will have time to present a very simple CBI-TCL based financial model. Very simple, actually, because actually it just corresponds to the processes that I have talked about before. X is an alpha CIR process, if you recall. This process, when we have the continuous part and we added to it a jump part characterized by a Lévy measure of alpha stable type, and the time change part is represented by just a Brownian motion here. And for technical reasons, we had to add a drift here, in particular to ensure that the exponential of z remains a martingale by means of this result, if we want to construct a financial model on it. Okay. Then in this case, just to convince you that we can, in very simple specifications, derive semi-closed forms for the principal characteristics of our CBI-TCL process, in particular the functions psi and phi, and also psi the Lévy exponent of this Lévy process, which appear in most of the results that I have presented. In this case, well, the time change part is quite simple, but the CBI part is more sophisticated than a continuous setting. And even in this case, we can compute in closed form or branching mechanism in the following form. Okay, but well, in this case, actually, we have some problems because the effective domain, which refers to the maximal domain of the convex function phi in this setting, is restricted to the negative real line. It satisfies the Maillard assumption, then we can apply the results. That we're gonna get only trivial results because it is restricted to the negative real line. In particular, it doesn't admit any exponential moments of any order. We have this at all times for all u strictly positive. But actually, we can circumvent this problem by adding a tempering factor to the Lévy, to the alpha stable Lévy measure, in particular an exponential, which allows to extend this set to beyond the negative real line. Okay. And then just to give, actually, even in this case, even in this simple specifications, we are able to derive the results, but we could have more refined results, let's say, with a more sophisticated specification. Then just to conclude very quickly, I would like to highlight what I have presented. A lot of things, but the principal parts are the following. First, we have the foundational results, which provide characterization, which means alternative definitions for Lévy processes, in particular by means of their extended Dawson-Lee stochastic representation. If you recall the R4 system of two-dimensional system of stochastic differential equations. And we have also preserved the affine property, which is crucial in financial modeling. And by departing from a more general affine process, we can recover a CBITCL process by means of by imposing some mild assumptions on the structural properties of the process. And regarding the results that we have derived, initially motivated by my financial modeling, we have shown that we can derive results on the finiteness of exponential moments of CBITCL processes, and also results on their asymptotic behavior, just by means of a very mild assumption. In particular, the one that I repeated several times, the finiteness of the derivative function of the branching mechanism at the boundary of its effective domain. And also, I had some time to present it. The identification of a class of CBITCL preserving polarity changes, which is crucial in particular to construct a financial model for exchange rate modeling. Okay. That's all. And this is our paper, still on archive, but in the process for publication in some journal of stochastic processes. Thank you very much for your attention.
Thank you very much, Guillaume. Is there any questions? Could I ask one? Is it possible to have with these kind of processes like a phase transition behavior? Isn't like, there's a certain, like, you introduce an order parameter, and for certain quantities it'll not explode or not grow exponentially, and for others it would?
What do you mean exactly?
So it's like this kind of, you said this in the beginning, this is a model of like self-excitation.
Yes.
So one thing I could imagine as like a property of self-excitation is that there's a certain critical regime above which it would explode in finite time.
Yes.
could you have the same kind of, could you create this behavior with the CBI-TCL?
Actually, it would require a more detailed study of its jumps. Actually, it has been done in the papers that I have mentioned at the very beginning of this talk. Just let me go back very quickly. Where is it? Yeah, these papers by Joe and co-authors in their last section. They provided a very detailed study of the jump behavior of the CBI process. In particular, if you remember the sample path, actually they have provided some results. For example, for the first time at which your jump go beyond some threshold, for example, they have results on this type. This is for CBI process. I don't remember if they had to impose some conditions at some point, but actually, in our case, we just built upon a CBI process.
Yeah.
Then I think we could extend this more detailed study, but it would require time and it's quite demanding. It's not that trivial. It could be possible. Yes.
These processes, I guess, so I'm not an expert on time changing, but I guess this is not very nice or easy to simulate. Can you comment on the reactive of these models and why, so how you approach them? Because it's not easy, right?
I presume they're not Markov, no?
Sorry?
They're not Markov.
I mean, they are not.
It's Markov because it's an affine process, and the affine process is Markov.
Okay.
It depends on which factor you say that it's Markov.
Actually, it's for simulating purposes. In our case, we didn't do it, but I have in mind some papers in which it has been done. I think it can be done in very simple specifications. Maybe if you have a time change Brian, it should be feasible. I don't know actually. It's hard to say.
Right. So I mean, I guess you lose the jumps.
Yes.
Not nice.
I think it could be done. We just have to keep in mind the Lamberti transform of the CBI process.
Yeah, what I mean is that you should every time point that you simulate, you should actually keep track of your x. And
yes.
In particular, this does not depend on the x at the previous time or something like that. Depends on the whole history, and every time you have to compute it.
Actually, you don't really need to. You can just replace this with this like a VT, which is defined as like the derivative of VT is x. It's the same way we do like with the Longevin equations. You extend it slightly to like.
Actually, as an example for this, I have in mind the simulation of a Hawkes process, which you can represent as a time change Poisson process. In this case, you have self-exciting structure. In particular, I proved in my I showed in my thesis that this is a specific. It reveals to be a specification on this setting. It definitely enters in this setting, and actually several authors successfully made simulations with this technique.
I guess otherwise.
Actually, we didn't try. I wanted to try, but we didn't do it at the end.
Speaking of Markov-ness, can you actually describe the generator of this process?
Yes.
Okay.
Yes.
Is it very ugly?
It's like, so you have the generator of the first Lévy, and then you have the generator of this time change.
Actually, so let me go back. Actually, you can derive it. You can derive it from this result. You show that it is an affine process. Then it is a Markov process with the generator exhibiting this specific form, a very specific form. You replace the parameters. I think you can have it.
Okay.
But I think maybe with the very Markov techniques, you can have it directly at the very beginning. You just need to know that if you remember, CBI process at the very definition is a Markov process. I didn't show it in this case, but we have a generator for the CBI process. And maybe you have techniques if you consider a two-dimensional process. In this case, you have the generator of this guy. You should just derive the generator of this guy. Maybe I don't know how to do it. I'm not an expert of Markov theory. I'm more oriented towards semi-martingale theory, but I think it could be a later topic for you.
Thank you. And we'll merci à